All right, so get this. We're going deep into 19th century geometry today.
Oh, yeah.
Yeah, and we've got some excerpts from the Stanford Encyclopedia Philosophy
Okay.
to, like, guide us. It gets
I bet it does.
really interesting. Imagine a world where um, rectangles just can't exist.
Whoa.
Yeah, or where parallel lines, like, decide to meet up at infinity. That's the kind of stuff we're going to talk about today.
So what's so fascinating about all of this is
Yeah.
how these shifts in geometry, I mean, they might seem kind of abstract at first, right?
Yeah, totally.
They really made philosophers rethink like some of their most basic ideas about,
About knowledge.
about knowledge itself. Yeah.
Okay, so Euclid.
Yeah.
Euclid, like the OG of geometry. I remember learning a lot of his postulates in school, but, like, can you refresh my memory? Why was that fifth postulate such a big deal?
Okay, so Euclid's fifth postulate, to put it simply, it sets up how we make triangles.
Okay.
It says, like, if you have two lines, right?
Mm-hmm.
And they're crossed by another line,
Yeah.
and the angles on one side add up to less than 180 degrees, well, those two lines, they're going to meet on that side.
Okay, yeah.
Yeah.
That makes sense. But I also remember that there was a lot of debate about proving this postulate, like actually proving it.
Right.
What was that about?
Yeah, so for centuries, mathematicians,
Yeah.
they were convinced that the fifth postulate, you could actually prove it from Euclid's other postulates, the ones that just seem so obvious.
Right.
They saw it as like a theorem
Oh.
that was just waiting to be discovered.
Okay.
But every time someone tried to prove it,
Yeah.
they ended up having to rely on assumptions that basically were just restating the fifth postulate in a different way.
Oh.
So it was like this circular trap.
So they were stuck, assuming the thing they were trying to prove.
Exactly.
And then Lobachevsky and Bolyai come along, and didn't they basically just chuck the whole postulate out?
Pretty much, yeah.
Really?
Yeah, they had this radical idea. What if we just like build a whole geometry where the fifth postulate is just not true?
Okay.
What would that even look like?
Interesting.
And that's how they came up with something called Lobachevskian geometry.
Okay, and what does that new geometry like? Tell us about triangles, lines. Does everything just, like, go crazy?
Well, things definitely get a little strange. Like in Lobachevskian geometry, the angles inside a triangle,
Mm-hmm.
they don't add up to 180 degrees anymore.
What?
Yeah, and get this. Triangles that are similar, like the same shape,
Yeah.
they're also congruent, so they're exactly the same size.
Wait, so if similar triangles are always the same size,
Yeah,
you can't scale things up or down, right?
right.
So something like a rectangle,
You got it.
it's not possible.
Rectangles just can't exist
Wow.
in Lobachevskian geometry.
My mind is blown. Okay. But if this Lobachevskian geometry is so different from Euclid's, how did mathematicians know it wasn't,
Yeah.
just made up nonsense?
Right, right. Well, that's where Lobachevsky was really smart. I mean, he didn't just invent this weird new geometry.
Yeah.
He showed that it was logically consistent.
Okay.
He said, like, if you find any contradictions in my system,
Yeah.
those contradictions would also have to exist in Euclidean geometry.
Oh, interesting.
It's what we call a relative consistency proof.
So it's like he was saying, if I'm wrong, then Euclid's wrong too.
Yeah, basically.
That's a bold statement. But did Lobachevsky think that, like, his geometry was the real geometry of, the actual space we live in?
Yeah.
Or was it more of a thought experiment?
I mean, that's a question that caused a lot of debate. Some
Yeah.
people thought that non-Euclidean geometries were just, abstract mathematical games like made-up rules.
Okay, yeah.
But others wondered if maybe, just maybe,
Yeah.
they were pointing to something deeper about the nature of space itself.
Ooh, interesting.
Yeah,
Okay, so now we've got Euclid and Lobachevsky, each with their own system.
yeah.
Where does projective geometry fit in?
So projective geometry, it's coming at things from a totally different angle, literally.
Really?
Yeah, instead of focusing on lengths and angles, it's all about the properties of shapes that stay the same,
Okay.
even when you project them. Think about like a shadow of a shape
Okay,
and how it changes when you move the light.
I got you, yeah. So what kind of problems does this approach help with? How does that make a whole new geometry?
So one big challenge in the older geometry was parallel lines never meeting, right?
Right.
In projective geometry, that's not a problem anymore.
Oh, really?
Yeah, because we add something called an ideal point
Okay.
to every line, and it's at infinity.
At infinity?
Yeah, and all these ideal points, they kind of hang out on this ideal plane way out there
Whoa.
at infinity.
So are we just, like, making things up to make the math work?
It might sound like that, but think about it this way.
Okay.
In projective geometry, parallel lines do meet.
Okay.
It's just at a place that's infinitely far away.
So we're just like extending our idea of space
Exactly.
to include these like points.
Exactly. Yeah, we're making it more complete.
And that has consequences, right?
Yeah, it does. It really changes how we think about things like uh, betweenness, you know?
Betweenness. What do you mean?
Like in projective geometry, points on a line are arranged in a circle,
Okay.
not a straight line.
Interesting.
So there's no real left or right,
Whoa, okay.
just a continuous loop.
All right, so that definitely challenges how we normally think about space.
Yeah, it's a big shift.
It's like our whole mental map is getting rearranged.
And here's another weird thing. In projective geometry, there's not really a difference between a point and a line.
What?
Yeah, you can think of a point as a line that's been like collapsed,
Okay,
or a line as a point that's been expanded.
interesting.
They're like what we call dual to each other.
Dual, like two sides of the same coin?
Yeah, exactly.
Okay.
And this duality goes even further. Points and planes, they're dual too.
Whoa.
It really changes how we think about these basic geometric elements.
Okay, so we've got these three geometries. We got Euclidean,
Yeah.
we got Lobachevskian, and we got projective, each with their own rules.
Yeah.
Did anyone try to, like, bring some order to all this?
Yeah, that's where Felix Klein steps in. He was brilliant.
Okay.
He tried to bring all these geometries together. He called it the Erlangen program.
How did he do that?
His big idea was to define geometry as the study of what doesn't change, what we call invariance.
Okay.
When you do things to shapes, like when you move them or transform them.
Okay, so can you break that down for me a bit? Like, what are invariants again?
Okay, imagine a triangle,
Okay.
right? No. Rotate it,
Yeah.
slide it around, flip it over.
Hmm.
Those are all transformations.
Okay.
Invariants are the things about the triangle that stay the same no matter what you do.
Okay.
Like in Euclidean geometry, no matter how you move a triangle, the angles always add up to 180.
Right, yeah.
That's an invariant.
So Klein was saying that different geometries come from studying different sets of these transformations.
Exactly.
And the things that stay the same.
Yeah. Euclidean geometry is about rigid motion, like translations, rotations, reflection, and their invariants. Lobachevskian geometry uses a different set of transformations.
Oh,
That's why invariants are different.
that's pretty elegant, actually. It's like
It is.
finding a common language for them.
It is, yeah. And what's really cool is that Klein's framework actually had implications for the real world, like in physics.
Really? So understanding the geometry of these transformations helped physicals understand, like, the universe better.
Absolutely.
Wow.
Yeah, like Minkowski, he was a mathematician and a physicist.
Yeah.
He used Klein's ideas to show how Einstein's theory of special relativity.
Right, the one about space is time and the speed of light.
Yeah, exactly.
Yeah.
He showed how it could be understood in terms of the geometry of something called the Lorentz group.
So geometry wasn't just about shapes on paper anymore.
Nope.
It was a tool to understand, like,
Reality.
reality itself.
Exactly. And as geometry kept evolving in the 19th century, it became really clear that, it was about way more than just shapes and measurements.
Yeah.
It was challenging our most basic ideas about space and knowledge and, like,
Mathematical truth.
yeah, mathematical truth.
This is some heavy stuff. We've gone from triangles to, like, the structure of reality.
We have.
I think we need a break.
Welcome back. We've seen how much our view of geometry changed in the 19th century, from Euclid's, seemingly perfect system
Yeah.
to the strangeness of Lobachevsky and the abstractness of projective geometry.
Yeah, I'm still trying to wrap my head around, like, points at infinity
Right.
and triangles that, like, don't add up to 180 degrees.
It's wild.
It is wild. But as someone who's, always been interested in philosophy, I got to ask, like, what did all this do to philosophers?
Oh, yeah.
Didn't Kant think that Euclidean geometry was, like, fundamental to how our minds understand the world?
You're right, he did. That's a really great question, and it gets to this huge crisis that these new geometries caused for philosophers. Kant, he believed that our minds, they structure our experience of the world based on these built-in categories,
Right.
and Euclidean space was one of them.
So when non-Euclidean geometries came along and turned out to be just as logically sound, that was a problem.
Huge problem.
Yeah.
It really shook things up.
Yeah, because if our minds are, like, wired for Euclidean geometry,
Right.
how could we even imagine these other, like, weirder geometries? It's like imagining a world where, up is down.
You got it. So philosophers had to figure out how to deal with this. Some of them, they argued that non-Euclidean geometries were just, formal systems like abstract games with their own rules.
Oh, okay.
They said that words like line and plane, they meant different things in these new geometries.
Okay.
So there wasn't really a conflict with how we normally think about space.
So it's like playing chess, but with slightly different rules.
Exactly.
The pieces have the same names, but they move in different ways.
That's it. But did everyone agree with this formal system explanation.
Not everyone, no. Some philosophers, like Poincaré, they took a more radical approach. They suggested that even Euclidean geometry might be a kind of convention. A convention.
Yeah, a useful tool,
Okay.
but not necessarily the only true way to describe reality.
Whoa, so geometry becomes more like a choice, a way of looking at things?
Right, and this led to a whole other debate. What is mathematical truth, really?
Oh, man.
Is math something we discover, like out there in the world?
Yeah.
Or do we invent it, like a language or a system of logic?
That's a huge question. How did mathematicians and philosophers in the 19th century even approach that?
As geometry got more and more abstract and more focused on axioms, it got kind of blurry.
Okay.
Remember how Hilbert said that we don't even need to know what points, lines, and planes are to
Yeah.
build a system of geometry?
Right.
That suggested to some that maybe math is more about playing with formal systems
Hmm.
than about reflecting like an objective reality.
So it's like we're messing around with concepts and seeing what kind of logical structures we can build.
Yeah, and not worrying too much about whether those structures like actually exist in the real world.
But even Hilbert, with his focus on these formal systems, he still thought that choosing the right axioms mattered, right?
Absolutely. He believed that good mathematical theories should be both consistent, meaning no contradictions,
Okay.
and complete, meaning they can explain all the relevant stuff.
So even if math is a kind of game, there are still rules.
Right, exactly.
But then how do we pick the right axioms?
That's the tough part.
Especially when geometry can be so flexible, how do we know which system actually describes the space we live in?
Ah, now that's where things get really interesting, because exploring these non-Euclidean geometries opened up this possibility
What possibility?
that the geometry of the space we live in, well, maybe it's not Euclidean after all. And this brings us to Riemann and his work on something called differential geometry.
Oh yeah, we talked about Riemann's idea that space could be curved, like the surface of a sphere.
Right.
But how did he actually develop that idea? And how did it go beyond what Klein was doing with the Erlangen program?
So Klein's focus on transformations and invariance was super insightful,
Yeah,
but it worked best with geometries that have a constant curvature.
constant curvature.
Yeah, like a flat plane for Euclidean geometry,
Okay.
or the surface of a sphere for elliptic geometry. But Riemann, with his differential geometry, he allowed for much more complex spaces, spaces where the curvature can change, like from point to point.
So like a landscape with mountains and valleys,
Exactly.
where the curvature changes depending on where you are.
You got it. And Klein-Erlangen program couldn't really handle this kind of variable curvature.
Why not?
It was based on the idea that a geometry is defined by one group of transformations,
Okay.
but in some of Riemann's spaces, there might not be any transformations other than the identity transformation that leave the geometry unchanged.
So in these weird spaces, even moving things around could change the geometry.
Exactly. So Klein's framework, which was all about finding things that don't change under transformations, it wasn't enough to deal with these more complicated spaces. Riemann had to come up with a whole new set of mathematical tools, tensors, metrics, connections to describe these curved things, these manifolds.
This is making my head spin a little, but I see how Riemann's work was a huge step forward. Like he was exploring uncharted territory, mapping out this whole new mathematical landscape.
I like that. That's a great way to put it. And what's even more amazing is that this abstract math exploration ended up having big implications for how we understand the universe.
Right, you mentioned that Riemann's ideas about curved space were crucial for Einstein's theory of general relativity.
Exactly.
But before we go there, there's one more thing I'm curious about those Lie groups. They sound kind of intimidating.
They do sound intimidating, but they're actually really cool. A Lie group, it combines the idea of a group, which we've been talking about, with the idea of a smooth manifold, which is like that generalized surface we've been discussing.
Okay, can you remind me what makes something a group again? All these math terms are starting to blend together.
Sure, a group is a set of things plus some operation that combines them, like addition or multiplication.
Okay.
And this operation has to follow certain rules, like associativity and having an identity element and inverses.
Okay, got it. So a Lie group is a group where the elements are also points on this smooth manifold.
Exactly.
Okay.
And the group operation has to work smoothly with the structure of the manifold.
Can you give me an example of a Lie group? It's easier for me to understand when I can picture it.
Absolutely. Think about all the rotations you can do in three-dimensional space.
Okay.
Each rotation can be represented as a point on a sphere,
Mm-hmm.
and combining two rotations, it's like smoothly moving on that sphere.
Okay, so it's a group where the elements are geometric transformations, and the group operation is like putting those transformations together.
Exactly. And Lie groups are so special because they connect abstract algebra and geometry.
Okay.
We can study symmetry and continuous transformations in a powerful way.
And how do Lie groups relate to all this 19th century geometry we've been talking about? Did they play a role in Klein's Erlangen program or Riemann's differential geometry?
Actually, they're connected to both. Lie groups gave a deeper understanding of the groups of transformations in different geometries,
Okay.
and they were also key to developing the math tools needed to study those curved manifolds that Riemann was working with.
So they were like this missing link, bringing together all these threads of 19th century geometry.
I like that. That's a good way to think about it. And what's even cooler is that Lie groups ended up being really important in physics, especially in things like quantum mechanics and general relativity.
It's amazing how these abstract math ideas turn out to be so important for understanding the physical world.
It really is. It shows how powerful math can be in revealing connections and patterns that we'd never see otherwise.
Well, I'm definitely starting to understand why 19th century geometry was such a revolutionary time. It wasn't just about finding new shapes and theorems, it was about a total shift in how we think about space, knowledge, and even the connection between math and the physical world.
It was a big change. And this new way of thinking opened up so many possibilities for scientific exploration in the 20th century.
I'm excited to hear more about those possibilities, especially how Riemann's ideas about curved space led to Einstein's theories of relativity.
We'll dive into those amazing connections in the next part of our deep dive.
Welcome back to our deep dive into 19th century geometry.
It has been a wild ride.
It has. We've gone from non-Euclidean spaces to projective planes and Riemann's curved manifolds.
Yeah, and like we talked about earlier, this mathematical revolution had a massive impact on physics, especially when it comes to Einstein's theories of relativity.
Right. I mean, it's one thing to say space can be curved.
Right.
It's a whole other thing to apply that idea to the actual universe and use it to explain gravity.
And that's what Einstein did. He combined Riemann's differential geometry with his theory of general relativity.
Okay, so for those of us who aren't theoretical physicists,
Yeah.
can you explain that? How does curved space explain gravity?
So Newton thought that gravity was this mysterious force
Yeah.
acting across huge distances instantly.
Right.
But Einstein, he proposed a totally different idea.
Okay.
He said gravity isn't a force at all.
Really?
Yeah, it's a consequence of the curvature of space-time itself.
Hold on, space-time.
Mm-hmm.
So we're not just talking curves to space, now we're talking curved time too.
Exactly. Einstein unified space and time into this four-dimensional thing
Okay.
called space-time, and he said massive objects like stars and planets warp the fabric of space-time.
So instead of the Earth pulling on an apple with some invisible force,
Yeah.
it's more like the Earth creates a dip in space-time, and the apple is just rolling down into that dip.
That's a great analogy.
Okay.
It's the curvature of space-time that determines how things move.
Wow.
The apple's not being pulled toward the Earth, it's following the shape of space-time, which is warped by the Earth's mass.
That is mind-blowing. So Riemann's mathematical ideas about curved spaces,
Yeah.
they actually gave us a way to understand one of the most fundamental forces in the universe.
It's incredible, right? It really shows how connected math and physics are.
It makes you wonder what other abstract mathematical ideas are out there
Yeah.
just waiting to be applied to the real world.
Absolutely. Throughout the history of science, we've seen tons of examples where math ideas that seemed purely theoretical turned out to be hugely important for understanding the universe.
Okay, so we've seen how Riemannian geometry changed our understanding of gravity.
Right.
But what about Lie groups? Where do they fit in?
Lie groups are central to both special and general relativity.
Okay,
Like in special relativity, there's this thing called the Lorentz group, which describes how things change when you switch between different inertial frames of reference.
okay, remind me what those are again.
Sure, imagine you're standing still, and then imagine you're on a moving train.
Right,
Those are two different inertial frames of reference.
okay.
Special relativity is all about how measurements of space and time are different in these different frames.
Right, and you're saying that this Lorentz group, it describes how those measurements transform as you go from one frame to another.
Exactly, and the Lorentz group, it's also a smooth manifold.
Oh, wow. So we can use Lie group theory to analyze special relativity itself.
You got it.
So Lie groups help us understand not just the transformations themselves, but also the geometry of space-time.
Exactly, and in general relativity, Lie groups also help us describe the symmetries of space-time and how physical things behave under those symmetries.
This is getting pretty complex, but I'm starting to get a sense of how all these mathematical concepts we've been discussing are really important for understanding the universe at a fundamental level. So for our philosopher friend listening along, what are some key things they should take away from our deep dive?
I think one of the biggest things is that our intuitions about space and time, which come from our daily life, can be very misleading.
Yeah, definitely.
Non-Euclidean geometries and Riemannian geometries showed us that space and time can act in ways that are much more complicated and strange
Right.
than we usually
It's
think.
like our everyday view of the world is just a tiny part of the picture. There's so much more underneath, and math gives us the tools to explore it.
Yeah, I like that. And another really important point is that even abstract mathematical concepts can have huge effects on how we understand the physical world.
That's been a recurring theme throughout this whole deep dive.
Right. The development of differential geometry and Lie groups, which might have seemed like purely theoretical exercises,
Yeah.
they turned out to be essential for understanding gravity and the nature of space-time.
It's wild how exploring math can lead to those kinds of breakthroughs in physics.
It is. It really shows the power of human curiosity and how all knowledge is interconnected.
This deep dive has definitely broadened my understanding of geometry and its impact on physics.
Me too.
I think I'll be thinking about curved spaces and Lie groups for a long time.
I bet you will. It's an amazing area of research with new discoveries being made all the time.
Any final thoughts for our listeners before we wrap up?
Yeah, I'd say keep asking questions, keep exploring, and never be scared to challenge what you think you know.
I love that.
The world of mathematics, just like the universe itself, is full of amazing things waiting to be discovered.
Well said. Thanks for joining us on this incredible journey into 19th century geometry. Until next time, keep those minds curious.